This is a video for AQA Further Pure Mathematics, Matrices, section 4.2, which is looking at factorising 3x3 determinants. You should already be familiar with the row and column operations that we've discussed for matrices in general. Indeed, so that the determinant of a transpose matrix will be equal to the determinant of the matrix itself. We can interchange rows and columns and then get negative of the determinant. Or we can add and subtract rows and columns, which produces a new matrix where again the determinant is equal to the original determinant. Or we can multiply a row or column by a scalar quantity, which then means that the matrix itself will have a determinant which is that scalar multiplied by the original determinant. These ideas can be used to factorize an algebraic expression which has been given in the form of a determinant. So the idea is that we use row and column operations to produce a row or column where the elements all have a common factor. Let's just look at this algebraic determinant. And I think you can see that if you take row 2 and row 3 and add them to row 1, then all the elements in the top line will be A plus B plus C. The other lines, of course, will be the same, C, A, B, and B, C, A. That means we can then factor out that expression A plus B plus C, leaving us with the determinant 1, 1, 1, and C, A, B, B, C, A. This is relatively straightforward to find because each of the elements in the top line are 1s. So we get A plus B plus C as our factor here. And then the determinant of the rest will be 1 multiplied by the determinant of A, B, C, A. That's this block here. So that will be A squared minus BC. We'll then have minus 1 multiplied by the determinant of CB and BA. So that is CA minus B squared. And finally, plus 1 multiplied by the final little 2 by 2 determinant, which is C squared minus AB. And that then can be simplified, and I'll do that on the next slide. So here's what we've done so far. We use the row operations to produce the first row with a common factor A plus B plus C, and have factorized that out to give the determinant here, and evaluated that determinant. There's an alternative way of evaluating that, which would be to subtract, for example, the first column from each of the other columns, and that would produce a matrix with 1, 0, 0 in the first row. So it would give us the first column as 1, C, B, and then A minus C, and C minus B, and B minus C, and A minus B in those elements, and that's a relatively straightforward determinant to evaluate. So different ways of finding that 3 by 3 determinant. However, when we do that, you can see that we've got these elements which simplify to A squared, and then we've got plus B squared plus C squared, and finally the little multiples of the other elements, BC, AC, and AB. So minus, in the bracket, AB plus AC plus BC. So quite a complex expression, but you can see that when it's written as a determinant, nicely straightforward here. So remember that the idea is to use row and column operations to produce a new determinant which has got a common factor in either a row or a column, which can then be factorized out. You might be able to do that with several different times, but finally producing a determinant that you can evaluate straightforwardly so that we get the factors coming out from our expression. In the next video, we'll be looking at how we use the factor theorem to determine some of those factors.